This is the lesson from Chapter 8 on bond energies. We will become very familiar with covalent bonding when we do Lewis dot structures. But as a reminder, when electrons are being shared, what can be formed are either single, double, or triple bonds. A single bond is the sharing of one pair of electrons or two electrons. A double bond is the sharing of two pairs or a total of 4 electrons. A triple bond sharing of 3 pairs or 6 electrons. All halogens form single bonds. Hydrogen only forms single bonds. So if hydrogen is bonding with fluorine, they will be sharing one pair of electrons, which is shown by a single dash. Carbon can form the variety of bonding that it does because it can form not only single bonds, but double bonds, which would be shown by 2 dashes, sharing of 2 pair, and triple bonds, 3 dashes, sharing of 3 pairs. The bond energy values. I have the table that is from your textbook, which is found on page 362. These values are experimentally determined and reconfirmed. Bond energy, remember, is the energy that is required to break a chemical bond, or the energy that is released when a chemical bond is formed. So they're usually from the perspective of what needs to be inputted to break the bond, which would be all positive because that's an endothermic process. The value of the bond energy is determined, one, by how many pairs of electrons are being shared, as well as the distance between your ion centers or your atom centers from the pairs that are being bonded, shared. For example, if we look down this little bit of sample bond energies, hydrogen is single bonded to hydrogen, but then our halogens. Now we know that fluoride, or fluorine in this case, is definitely the smallest, iodine being the largest. We see our bond energies decrease because these shared electrons are much further from the pole of the nuclei of iodine than fluorine. Thereby, it's much easier to break this single bond than it would HF. If we look at multiple bonding, carbon sharing a single pair of electrons with carbon requires only 347 kilojoules for every 1 mole to break, where when we increase the amount of electrons that are being shared, we increase the bond energy. We increase the strength of what is actually holding these together. Remember in Chapter 6, a goal of ours was to determine the enthalpy of reaction for a process. Well, we can actually use bond energies to determine the enthalpy of the reaction. And so this will be one application of bond energies. The enthalpy of the reaction can be found by adding up the bond energies of the reactants, which what we're going to end up doing is breaking all of these bonds usually, or the grand majority of them. So here's an endothermic cost. And if we add all of the energies that will be released when our new bonds are formed, but take them to be negative because that energy is being released, that will give us the enthalpy of the reaction. Or we could just add up the bond energies of what is required for breaking and subtract that from the bond energies that we know will be released when these are formed. However, if we make it negative, then that will take on the exothermic nature. So let's show this with an example. Again, we will get much more familiar with just knowing the type of bonding that is present in a formula after we do Lewis dot structures. Methane is reacting with chlorine and fluorine to produce freon. The question is, what is the enthalpy of the reaction using bond energies? You would be provided these in the problem or a table to get them from. Methane is made of carbon that is singly bonded to 4 hydrogens. Chlorine is single bonded to chlorine because that's all that halogens can do. Fluorine is single bonded to fluorine. We are making freon, which will be carbon, and doesn't matter where we put our chlorines and our fluorines, as we'll see with single bonds, there's total rotation. We'll get more into that. HF and HCl. All right, now, if we see these are reactants to products, we need to break every single one of these single bonds, because on this side there isn't one carbon-hydrogen single bond. Now if we look at our balance equation, we need 1 mole of methane and each of these bonds to be broken. So we need 4 moles of carbon-hydrogen bonds, because there's 4 carbon-hydrogen single bonds here in 1 mole of methane. We are also in need of breaking the chlorine-chlorine bonds. I don't see any chlorine-chlorine bonds here that have retained themselves. And there's 2 moles per our balance equation. So we have 2 moles of chlorine-chlorine that we're breaking, and the same with the fluorine. 2 moles of that, and I don't see any fluorine-fluorine single bonds on the product side. On the reactant side, all of these bonds are being made, and I need a coefficient of 2 and coefficient of 2. So I have 2 moles of carbon-fluorine that I'm making, 2 moles of carbon-chlorine that I'm making, 2 moles of hydrogen-fluorine, and 2 moles of hydrogen-chlorine. Our bond energies, if we go and obtain them, for the carbon hydrogen, it's 413 kilojoules per mole, so I'll need to multiply by 4. The chlorine-chlorine is 239, and the fluorine-fluorine is 154. When I do all of this and add them, then I get a total of 2436 kilojoules of, this is from the bond energies of what must be invested for the broken bonds. Broken bonds. For the carbon-fluorine, 485 kilojoules per mole. Chlorine-chlorine is 339. HF, 565. And HCl, 427. Doing all the multiplication and then adding these, again, these are the reactants and products, I receive 3632 kilojoules total. So, the enthalpy of my reaction, okay, this is what must be invested, 2436 kilojoules. If I want to subtract or add the negative, because this is what's going to be released, then the enthalpy of the reaction here is negative 1,192 kilojoules. And it's just saying the enthalpy of the reaction, so this would be per the balance equation. Or, as we saw in Chapter 6, the enthalpy would be reported for the reaction to be negative 1,192 kilojoules. That's how we use bond energies to determine the enthalpy of reaction.